said NaOH was the one that we should use. But if we change the reaction to instead produce this product, we switched it up to something else. What did we switch it to? We now said sodium hydride. And the question that we then projected was, well, aren't those the exact same products? Yes. So why are we getting a different reagent to do each of these reactions? Say that again? We're looking at reversible versus irreversible. So depending on what we're trying to do, we may need to use a different base. Okay? And because I'm all about color coding, we'll switch that out. If we were going to run, say, our blue reaction, we're going to use that weaker base because I want some of the starting acetone and the starting enolate. Okay? I want a mixture of both of those. That's why I want to use sodium hydroxide. If instead I only want the enolate, well, now sodium hydroxide doesn't work because it's only going to be the sodium hydroxide is going to generate an equilibrium. So I would need to switch to sodium hydride. So depending on what I'm trying to do, I need to be very cognizant of what base I'm using. Okay? As a general rule of thumb, we end up using the weakest base that does what we want to. Why? Why? No. It doesn't really have anything to with dissociation because I could decide sodium hydride is what I have to use. That does fully dissociate. Close enough. We'll cross that bridge later.
Why handle more corrosive things when we have to?
Minimize safety or minimize safety issues. So I want to use the weakest base that still does what I want to do so that way I'm not dealing with a whole bunch of extra waste. Okay? As either a cost thing to deal with the waste or as a safety thing that I'm dealing with toxic chemicals. Okay? So a lot of the chemicals that you see listed for particular reagents or reactions are chosen because of that. We have lots of different bases we could choose from. At any given instant, we may be choosing one over another because of those secondary considerations. Those secondary considerations are often not shared. Okay? So let's switch it up. What base should I use for that reaction? I can make it easier potentially. What's that?
Sodium hydride.
Sodium hydride. Why did you jump to sodium hydride?
Because the arrow is only going in one direction.
We said one direction, we want to maximize the crap out of it. Let's go all the way out. Sodium hydride is a phenomenal one that will work to do this. It is not the best choice. Okay? So it will absolutely do this reaction and a bunch of others. It'll probably also deprotonate out on the edges too, in some limited cases. Okay, the base that we want to choose to run this reaction, sodium hydroxide. But wasn't that one the weakest one? Didn't that cause an equilibrium issue with acetone? Why can we get away with sodium hydroxide now to run this reaction? What do you got?
I was going to say, the first one seems like it's a resonance structure, right?
The first one, these aren't resonance structures. There is a resonance contributor that would stabilize, okay? And that's why we can use sodium hydroxide, okay? Why that hydrogen was acidic to begin with. The second one, why can I use a weaker base? Close. What's it in it's stabilized by induction?
The negative charge.
Okay, so you're referencing that material, which is a good thing. That's what's ultimately changed here. Okay, we draw up our sodium hydroxide for both of them. The blue sodium hydroxide resulted in an equilibrium. The red one is unidirectional. Okay, there is some more stabilization of that conjugate base, okay, through, your suggestion was induction. Does everybody agree? Is it induction that stabilizes that conjugate base?
There's resonance as well.
There's more resonance. This has 2 resonance directions. This one only has 1. Okay? That more resonance stabilizes the conjugate base. If we have a stable conjugate base, what does that mean about the acid? It was stronger. That compound, our starting material there, is so much more acidic than our acetone. All I need is sodium hydroxide to fully deprotonate it. Okay? That's why we use sodium hydroxide. The acidity has changed that much. Okay? So it isn't just, I'm always going to use one base or another. We also have to consider the other half every single time. Kind of make sense? Okay. So we're going to start into our substitution and elimination. There was supposed to be a whole bunch of play posits for each of these. I think the only one I've got as a play posit is the substrate. There is a leaving group nucleophile base and solvent YouTube video, which I don't think I've got linked yet, but I'll try and get those linked in there. Okay, so let's take a look at those structures. Which of the following could be a substrate? We'll simplify a little bit. A, B, C, D, E. Substrate as a term, we tie to which reactions? Substitution. Okay. What functional group do we typically tie to substitution reactions at this stage in the game? Particularly because half the class had OChem 1 with somebody else. Alkyl halides are typically our substitution substrate. Okay. Which of those is an alkyl halide? Which of those could be a substrate? A, fantastic, I like it. Where in A is the substrate chemistry? Okay, so if we break this down further, 1, 2, 3, 4, and we're going to be extra irritating, 5, 6, 7. 7 different locations that could be our substrate chemistry. Where's our substrate chemistry? The carbon-bromine bond. So you didn't need me to number it. Thanks for making me number it. Position 3 in our list. Okay. That carbon-bromine bond is likely to be the weakest bond in that structure because a large difference in electronegativity between the carbon and the bromine. Bromine's more willing to take those electrons, making that carbon very partially positive and susceptible to something coming in and attacking it. That something would be a nucleophile, and we would have a nucleophilic substitution reaction. Okay, so that would be a reasonable place that we could have a substrate reaction. Okay, how about the next one? B. Yeah? Give me more.
OH?
No.
Okay. So Lee's already saying no. I like where you're going with that. It's definitely a good place to start. Why are you saying no?
Wait, is not good link.
Say that again. OH is
not good.
not a good leaving group. Okay. So you're addressing the OH. Okay, and this is where we might need to be a little bit more careful. Is the OH what we should be circling to reference the substrate? The substrate is where the leaving group left. So the OH is a good place to zero in. Oxygen being very electronegative, fantastic place to zero or keep our focus on it. Okay, but it's not the OH that makes it the substrate. It's the carbon where the OH is connected that makes it a substrate. Lee has a good extra point to add to this. Okay? In our substitution reaction, we have to have a leaving group. Is OH a good leaving group? to be a good leaving group, it must be stable on its own. My general approximation is run a face test with it. Okay, and everybody kind of grimaces if they heard it before. They haven't heard it before, they think it's just weird. Someone takes hydroxide and throws it in your face. Are you happy? Okay, or at least just like, don't do that, please. Okay, you're probably going to be very, very unhappy as your face melts. That's not a good leaving group. Okay, a good leaving group should be, stop getting me wet. Like, that's kind of irritating. Leave me alone. Okay, make sense? Hydroxide does not pass the face test. That's a horrible leaving group. Does that mean that carbon isn't a substrate? No. What would have to happen first?
You have to prepare it.
I might need to add a hydrogen to that oxygen to now make it a good leaving group so that the carbon can act as a substrate. So when we're looking at a structure, we're thinking about those basic patterns of what fits for a substitution reaction, where and how. Okay, that next one adds on that layer of how. Lee's right, that's not a good leaving group. But if I make it a good leaving group, now it can be a good substrate. Make sense? Why does that help me? This can help me now predict chemistries. Maybe I know that carbon needs to have something happen to it. Before that can happen, I have to make the oxygen a good leaving group. Maybe the first step of my reaction is add an acid. I now have something to predict and help me know those reagents to move forward. Okay, how about the next one? You can always say no. This would be a good example. No. This is not a good substrate. Okay? Way too many bonds to go through and break to have it act as a substrate. We don't have anything to really stabilize charges within that. Okay? So that's not very good. What it is really good at, with a little bit of resonance, what can we do? That carbon can become negative, which means it could donate electrons, which means it could be a nucleophile. Nucleophiles react with what? Technically substrates, yes. Technically electrophiles, yes. Would I say a nucleophile would react with a H+?
Yeah.
Remember, we went
No.
through specifics on that. No. Nucleophiles react with anything that is specifically not hydrogen. Because if it is hydrogen, it's not a nucleophile, it's a base. So we really want to be careful in that distinction. Okay? So to act as a nucleophile, it has to react with something that's not hydrogen. Where is not hydrogen found?
Substrates. Everything with acids.
Where in and everything?
Inside.
Inside a structure. What's on the outside of that structure?
Hydrogen.
Hydrogens. That becomes very dangerous for a negatively charged species. For it to act as a nucleophile, it must get by hydrogens. If it sees the hydrogens, instead of acting as a nucleophile, it acts as a base. What's going to be the defining factor that allows us to differentiate nucleophile versus base?
Size.
Size. The larger it is, the less likely it will make it to the inside, which then means it can only react at the outside. The only thing on the outside is hydrogen, which is why it acts as a base. Okay? This is dBu or dBn, something like that. Very commonly used as a base. Okay? Next one. What's that? Yeah? Where?
The carbon to the
Left?
the chloride.
That one?
To the,
Okay. Why?
because it can leave.
Phosphorus may not want to be positive, so the phosphorus could leave. Okay? So there's a potential site for it to act as a substrate. Does it act that way? No. Do you need to worry about it? Not yet. Okay? But what we're trying to do is pick out those places that stand out as potentials. How about the last one?
It's a good something, but not a substrate.
Yeah, this is
Why is it not a good substrate?
No carbons?
Okay, this is organic chemistry. We need to have carbon. Do we? No. At the heart of a substrate, what must happen?
organic reaction.
What happened over here to make that carbon a substrate?
We substituted.
Broke a bond.
We broke a bond. Okay, so we broke that bond?
No.
No. Okay, what bond did we break?
We broke a carbon-bromine bond
Why did we break a carbon-bromine bond?
because the high electronegativity difference between carbon and bromine made it
Large difference in electronegativity. Bromide was really stable as a
Ion?
ion, which true. I was fishing for a different word, but yes. Leaving group. Do we have bromide? Could one of those bromines act as a leaving group? Yeah. Could that potentially act as a substrate? Could a nucleophile attack it? Yes. The phosphorus can be attacked. We can eject a bromide. You might be, well, it has electrons. It has a lone pair of electrons. Phosphorus should not act as a substrate if it has a pair of electrons. It has 3 very electronegative elements attached to it, all of those withdrawing electron density. Okay? That can cause phosphorus's electrophilic character to go up enough that it could potentially act as a substrate. Is it an organic substrate? No, because we made the very good point that it doesn't have carbon and hydrogen. Does that mean we won't see it? No. In fact, we'll see that in chapter 11, 10, chapter 10. Okay? Kind of makes sense? Get the idea for the patterns of what you need to start looking for when you think about these terms. It's not just, oh, a substrate is this. What do those different things look like? Okay, where's the leaving group? We already started to address this. The bromine in the first one was a leaving group, okay, which we said was a good leaving group because
Stable.
it's stable. It would pass the face test. You might be, well, it's negative. Isn't that bad? Bromide is more or less stable than chloride. More stable. Why?
Bigger?
Bigger. Okay, the very second thing in our list, charge, size. Are we concerned about chloride?
Yes.
Yeah? How many of you have cried? What is in your tears? Chloride. Is your face melting off with the chloride? No. Despite how it feels. Bromide's a more stable structure than the chloride. If we aren't panicked about the chloride, we aren't panicked about the bromide. Okay? You might be thinking, well, hydrochloric acid, yes, that is an entirely different substance. And hydrochloric acid, I'm not concerned about the chloride. What am I concerned about? The hydrogen of hydrochloric acid. Okay? Which is active as an acid because
It's so unstable.
chloride is so stable. Conjugate base. Okay? Leaving group in the next one. Said was the hydroxide. We could now bring in the extra question of, well, is it a good leaving group or not? Okay, if it's not a good leaving group, I need to make it better. Right now, theoretically, everybody's on the same page. The only way we can make leaving groups better is to add a hydrogen to them. Okay? Depending on your background, you might have more experience with that. Okay? The next one we didn't really say was a substrate. The next one we had that phosphorus. Why did we pick the phosphorus as a good leaving group?
Because it was positive.
It starts positive. If it left, it would become neutral. Less charge is better. Okay? Last one, we said bromide is a leaving group. We already addressed that with the first one. Make sense? So you're trying to identify those pieces of your reactions. Okay? Nucleophile, base, or both. First one. Okay. Why would we ask nucleophile and base in the same sentence? Because of the rules you gave us. Yeah.
Because both of them donate electrons, we're just trying to figure out what they're going to donate electrons to.
Both of these donate electrons. Nucleophiles donate the electrons typically to carbon, but really anything. We'll just say any. And bases donate electrons to hydrogen. Okay? Why does this now become a tricky question? Well, do you see what they're reacting with? No. So you have to try and make some approximation based off of what you're seeing here to decide, could it react in both situations? Okay. First thing we might look for would be a charge. Why is that first one tricky?
Because it's not apparently charged.
We don't see the charge. It is super common for students to look at that and be like, oh, well, that's not common. We don't need to worry about that. That can't possibly be what the question is asking. Added to that, we throw it in as lithium, and what are you used to seeing it as?
Li+.
What are you used to seeing instead of lithium?
Sodium.
Sodium. Same chemistry. Okay? So just a simple change in the atom can now make this question go, oh, I have no idea what's going on with it. Okay? Break it down into the basics. What we're looking at there is really ethoxide. Base or nucleophile? Okay? Nucleophile. Why? It can donate electrons. Can it donate electrons to hydrogen?
Yes.
Yes. Okay? What have you got?
It's small. It's not a bulky.
It is on the smaller end, so it could act as a nucleophile. Just because it's small doesn't mean it doesn't act as a base. It just means it now has an increased chance of acting as a nucleophile. Ethoxide can be very tricky. You'll usually get both. How about the next one? Why is that one only a base? Now, since it's big and bulky, that prevents it from acting as a nucleophile. Sodium hydride.
That's a big. No, it's both.
Okay, both. Why do you say both?
Because the hydride can obviously donate to hydrogen.
Obviously donate to hydrogen. Does everybody agree? Obviously donate to hydrogen?
Yes.
Okay.
But it's also small, and so it can get in there, and then if you've got like a positive, if you've got a carbocation and you put in sodium hydride.
Everybody agree with that? Everybody hear that? It's small. That is the smallest that we could possibly get. Cool. Very phenomenal reasoning. It's also wrong. On the list here, sodium hydride is the largest of all of those. Really? Anybody want to go out on a limb and like agree with me? Or are you just going to be like,
And we're going to wait for you to explain that one.
wait for that one to come out? How stable is hydride? Not. Okay. So incredibly unstable that it is glommed onto the sodium. It will not stabilize nicely in solution. So what happens? It stays a solid. That one is large because of a phase difference. Sodium hydride stays a solid. Because it stays a solid, it is now literally the largest thing we could possibly get because it doesn't go into solution. The only place that we can react sodium hydride is on the surface of the material. Chemicals are a lot smaller than the surface of, say, like a table. Okay? That means sodium hydride is actually the biggest thing here. It acts exclusively as a base. Okay? That is an exceptionally tricky one for that reason. Bromide has electrons, right?
Yeah.
So it could do both, right?
No,
Why not?
because it's so stable on its own, it's not going to pick up hydrogen.
Okay. So stable, well, if it's so stable on its own, shouldn't it not react as a nucleophile?
If you've got a better leaving group of bromine, then
The best way to look at this one, what would happen if bromide acted as a base?
you get HBr, which disassociates.
Okay. And now we're going to fish for some keywords not from David. What is HBr? I don't accept acid. It is a strong acid. by definition, it completely dissociates when it forms. Okay, which means you can't form it. Okay, if you can't form it, then bromide can't act as a base, because if it did, it would have to make that strong acid. Okay, there are very few species that act only as nucleophiles. Your halogens are them. Okay, those are pretty much the only ones that can act solely as nucleophiles. Okay, kind of makes sense? Cool. Classify the following. What are all of these things? Did you say you hate this question already?
They're solvents.
These are all solvents, okay, which personally I have problems with as well. Okay, I tend to not ask a lot of solvent questions, so if you were in previous classes where you had to include the solvents, yes, they're important. Yes, they should be included, but I probably won't grade you on it. Okay, but you should be able to look at a solvent and tell me something about it. Okay, there are three primary categories for our solvents: protic, polar aprotic, and nonpolar. If you want a review of how those come about, that's what the solvent video is for. So what do you guys see? Not yet.
Let's start from the easy one.
Sure.
From the back.
Which one?
Cyclohexane, nonpolar.
Okay. Nonpolar. What makes that one, I think, a little bit harder? Or I think that's personally a little bit harder. You were all over that. Why is that one easy for you?
Well, it's a hexane. I mean, well, it's one of the anes, and all of those are nonpolar.
Okay, it's one of the anes. That's a good way to deal with this. Okay, and what you're referencing is nomenclature. To answer the question, you had to know nomenclature. Because if you knew nomenclature and that that's an ane and that just means carbons and hydrogens all singly bonded, those are all nonpolar bonds. There's nothing to cause that to be polar or protic. Nonpolar. Fantastic. What else?
Ethanol, polar product.
Okay. Where are you going with that one?
Oxygen, pulling
Where are you getting the oxygen from?
the all.
Which means? Okay, thank you, which means OH group.
Which means what is it pulls?
That means someone else.
Makes a pulse.
That's going to be protic, not polar aprotic. We have a hydrogen that is bonded to oxygen, nitrogen, or fluorine. That makes it protic. Your protic solvents are pretty much anything that can hydrogen bond. Okay, and really I should say hydrogen bond donors. Okay, alcohols by definition can donate hydrogens. Yes.
THF also protic because it has an H for bonding.
So we have to be careful on that. So when you say THF, it has an H for bonding. There is an H there. Does that H refer to hydrogen?
That's like a short name for a chemical.
It's the short name for the chemical. So what is THF?
Some long chemical.
Tetrahydrofuran. So the H is standing for a hydrogen, but I'd have to know where that hydrogen is connected within the structure. That's tetrahydrofuran. Okay? So yes, there are hydrogens. They're all connected to the carbons, though. If they're connected to the carbons, are they hydrogen bond donors? No. So we have to be careful. Just because you see the H next to the F doesn't mean that was an actual connection. Okay? That's why I threw that one on there. Yep. It's also why I don't like solvents. Okay? So THF then, I don't know why I pulled that board down. I looked at that one. So looking at the structure of THF, what do we think? Protic, polar, aprotic, nonpolar? Polar aprotic. It is polar because it has that electronegative oxygen, but we don't have a hydrogen connected to it, so polar aprotic. And then the middle one? Okay, that is aprotic, so we're not in the protic column, so now is it polar or nonpolar? It's polar. So polar aprotic. Why is it polar? The oxygen. That's pretty much it. You see the oxygen, you're there. Okay? That solvent is also commonly known as a hint, I could have done that instead of THF. I went back and forth with those two. DMSO. Okay, is typically how that one shows up. Okay, kind of makes sense? So these would be the basic pieces that we could use in, say, a substitution reaction, which would get us to our big summary slides. Okay, I'm not going to talk a whole lot theoretically about the next sequence of slides. These are here primarily as review things to help you kind of centralize and compartmentalize this stuff. So feel free to download those slides and print them. But what they're doing is categorizing our two substitution mechanisms, SN2 and SN1, and summarizing all of the big things that get associated with those two mechanisms. Okay? I did also attempt to put it in an order that I think is most relevant to look at. For me, when I look at those mechanisms, I look at the substrate first. I zero in on the substrate and I say, well, what is it? Okay? How does that help me decide which mechanism? Okay? So what we can do is add something else to this. It should be in here, but I didn't put it in there. Would be like a keyword. Okay? So if you memorized substrate, nucleophile, leaving group, and solvent, those are the components to these, and you've got memorized SN2, SN1, we need an extra bit of information so that we can help piece these things together. What would be a key word or words that you should memorize for SN2? Backside attack. Okay. This means our nucleophile must come in from the backside. Okay. Our nucleophile brings in electrons, so what needs to be on the backside? Or rather, not on the backside?
Electrons.
Electrons, known as steric hindrance. Okay? So the backside attack is the non-science, steric hindrance is our science. If we move over to SN1, what do we need to memorize? Carbocation. So that when I look at a substrate, I need to be thinking about cation stability. Can I stabilize the cation? If I can, then that's a good thing for an SN1. Okay? Nucleophile. I need strong nucleophiles for SN2. Okay? I don't really care about the nucleophile in an SN1. Why do I not care about the nucleophile in the SN1? So we go all the way down to the rate law. And I look at my rate law. Do I see nucleophile in the rate? Nope. So I don't care about the nucleophile strength because it literally has no effect on the rate. Okay? Those of you that had not had me for OChem 1 or people that have had me and want a review, we can discuss about where those rates are coming from. Okay? There is solid science behind why these things come about, and it's all a mechanistic understanding, not just a rote memorization process. Okay? So each of these kind of terms that go through this helps you to distinguish between an SN1 and SN2. So that when you see a substrate, say like on the previous slide, you could try and go through and quickly classify that substrate. I know the chemistry is at that position. I know it's connected to only one other carbon. That means that that is a primary substrate. The primary substrate has virtually no electrons around it, which would mean that substrate should go under SN2 mechanisms. Okay? All of those thoughts should be stacking very, very quickly whenever you look at a structure. Okay? That takes practice, so don't stress if you aren't there yet. Okay? You probably won't be. You just spent all summer not doing this. Okay? You can do the same thing by looking at your nucleophiles or your leaving groups. The substrate pattern, I'm a little bit not liking inserting in this because people overuse the substrate pattern and go, oh, well, it's primary, so it must be SN2. Or it's secondary, it must be SN2. Or it's tertiary, so it must be SN1. Okay? There are other classifications on top of primary, secondary, tertiary. Like? That's primary, right? So we would say SN2 substrate, right? Is it still primary?
Yes.
It's still connected to one other carbon. So shouldn't that only be an SN2 reaction?
No, because you've got resonance contributor.
Resonance can contribute to these. Resonance contributes more to stability than just substitution. That's why when we look at our sequence of things to evaluate stability, we start with, we don't start with resonance, we start with charge, size, electronegativity, resonance, induction. Where did substitution come in?
Induction.
Substitution's in rule 6. That's the, oh crap, I've got to deal with something else. Okay? So that goes way out there. Resonance is a much greater effect. Okay? Why do we tend to not mention resonance when we're first looking at substitution reactions in first semester? Because students were so awful at it in the very first unit when drawing out resonance that we're like, we'll give them a break and we'll just look at these substitution patterns first. The problem is that then you'll only look at the substitution patterns. Resonance plays a larger role. Okay? Of course, it can't be as simple as just our SN1 and SN2. We also get elimination reactions, E1 and E2. So we'll get the same rough breakdown. Notice one big change here is instead of saying nucleophile, it says base. Why?
Because you're pulling off a hydrogen.
Because it's an elimination reaction, not a substitution. Okay? The slowest step is a different aspect of the reaction. Okay? The mechanisms or the reactions themselves run differently. You'll notice we also see some information about stereochemistry and regiochemistry. I really hate calling it Zaitsev's product, okay? But you're fine to do that if you really want to. Okay? We're ultimately looking at stability of pi bonds. Okay? Think about energy behind your reactions, not just the names of reactions. Okay. The last big thing that's probably for all of you who have not had Cardi. Cardi went through and organized this. I don't know why I never thought to do this, because we're similar in some other things. And just said, here's all the factors, here's all the reactions. Look at each one and decide. So with this kind of table, you could look at a reaction and be like, is there a strong nucleophile? Okay. In the case above, bromide. Is bromide a good nucleophile? How do I know that's a strong nucleophile? It's negatively charged. A strong nucleophile favors which mechanism? SN2. I can put a check mark there. Okay. You notice I have NAs under elimination. Why?
You don't use a nucleophile.
I don't want a nucleophile for the eliminations. Okay. So it's not relevant. I literally don't want them. Okay. We could go through and say strong base. Again, the NAs for substitution. Is bromide a strong base? It's negative. No, because it forms a strong acid. So what happens? I don't check anything. Leaving group. You notice I've got leaving group in really small font. I should actually drop it to the bottom because in order of priority, it's stupid to look at. When do you need a leaving group?
Whenever you want to substitute.
Whenever you want a substitution or elimination reaction, which means, do I have a leaving group? That's a pretty freaking useless thing to check mark off. Okay, that doesn't help us count anything out. Substrate. What substrate do we have? Okay, that's the name of it. Okay, I want to classify it. The chlorine is the leaving group. The substrate, okay, was there. That's got 1, 2 carbons connected. That's a secondary carbon. Which mechanism is favored by a secondary reaction? This one kind of sucks too, but for a different reason than the leaving group one. Okay. Secondary substrates are awful because everything will run in a secondary substrate. Okay, solvent. What's my solvent? DMSO. And conveniently, we just discussed that one. DMSO is aprotic, which favors SN2, or aprotic solvents are SN2. I'd be careful looking at solvents with eliminations. Okay, those can be a bit dicey or dodgy to deal with. Heat.
Doesn't say it.
We don't have anything specifying for heat. Heat is typically something we'd see for elimination reactions. Now what do? Well, I've got 2 check marks for an SN1. How many check marks for an SN2? 4, 2, 2. Which mechanism am I going to run? SN2. The table allows you to kind of organize your thought process so that you can solve it. Make sense? Not a requirement by any stretch of the imagination, but it's there to kind of help you process through that. Okay? Next kind of thing is, again, just breakdown for substitution elimination, how I go through and think about them. I know I said I look at substrate first. I actually don't. I look at the nucleophile first, okay, or that negatively charged species. I typically look there first because it is charged. It's the most reactive thing in the solution. That's where I'm going to spend my focus first. Okay? Because that's going to help me figure out everything else. Okay, so the strength of that species is going to determine the order. If it is strong, it's a bimolecular reaction. What do I mean? If I have a strong base, what do I have?
E2 reaction.
E2. I know it's type 2 because
It's a strong base.
strong. Because I said it was a base, I know
It has to be an elimination.
elimination. Okay? This becomes challenging because I have to differentiate between nucleophiles and bases. Okay? That's that line that we've been talking about. And it'll probably won't be that big of an issue this semester. It's more of a first semester distinguishing. Okay? Substrate structure. Okay? Primary halides is an awesome one. If you see a primary structure, that's really, really useful because almost universally that's going to run SN2. Okay? That is not favored in any other mechanism. E2s can happen with primary halides, but you have to have special conditions. What would the special condition be to force an E2 with a primary halide? Heat
Super bases.
and a base. We'd have to make sure that we have exclusively a base. Okay? Because if it wasn't a base, it could be a nucleophile, we'd see the SN2. Okay? Secondary halides really suck to deal with. Ultimately, go back to Rule 1 and hope Rule 1 solved it for you. Otherwise, you're kind of dead in the water. Or, on a multiple choice test, look for the all of the above answer. Okay? Tertiary halides get you a giant mixture, SN1, E1, and E2. Okay? Solvent, protic favors SN1, aprotic favors SN2. Okay? Eliminations are dodgy. Be careful with using solvents to predict an elimination reaction. Okay, and then the last thing I look for typically is heat. I'm not sure that's actually on here. Yeah, there it is. High temperatures favor elimination. In theory, that was all review. Yeah? You weren't like, damn, that was brand new material. Okay, that's all I'm kind of hoping for. Complications, there's some complications, of course, within each of those, stereochemistry, all that fun stuff. Okay, but now really what that's going to take us into is our electrophilic addition reactions. Okay, these are nonpolar pi bonds, primarily alkenes and alkynes. Okay, these are not reactive species. Why are they not reactive? What was that? I think I heard someone mumble something. They're not charged. Okay. But by that same token, neither is the alkyl halide. So I do accept charge as a possible explanation, but I could use a counterexample that is fairly reactive. That's so reactive that when that hits my eyes, I cry.
Because the electronegativity between the carbon and hydrogen bonds is less than carbon and bromine.
Okay. Carbon to bromine has a high difference in electronegativity. Okay. Interestingly, with the alkene, you reference the carbon-hydrogen bond not having a large difference in electronegativity. That's one of them, and the carbon-to-carbon bond has a very low difference in electronegativity. That makes the alkene and alkyne significantly less reactive than our alkyl halides. Okay? What makes the alkene reactive?
The electrons in the pi bond.
The electrons in the pi bond. Why the pi bond?
Because that's the only place you could get spare electrons versus bromine.
Pi bonds versus sigma bonds. Which are higher in energy?
Pi bond.
Pi bonds are higher in energy because they involve p orbitals, not s orbitals. P orbitals are higher than s. Okay, so it goes all the way back to atomic theory. Okay, so those electrons are accessible to react with, but I must polarize them to get them to react. That can either happen by adding a really strong acid or by adding a really strong electrophile. Cardi breaks this into 2 chapters: acid reactions and electrophile reactions. Okay? Big summary of all of our reactions. So when you see things like this, sorry, it's just giving me weird buttons. When you see things like this, what this is supposed to do is summarize all of those reactions. Unfortunately, I do need to redo it so I can organize it to match better to Cardi's standards. Okay? But what this shows is all of the reactions for our alkenes, all in one diagram. Should you know all of those reagents already?
Yes.
Yes. Those are all first semester reagents. You should know what every single one of those does. If you don't, that's okay. You've got it 4 weeks. 4 weeks, because that's our first exam. Okay? So work towards that. Okay? But in that process, it's not just, oh my God, I got to memorize that structure, because I get students doing that. And then I change the structure to a cyclohexene, and now you can't do it. Oh my gosh, it's 6 carbons. The chemistry is the pi bond. I don't care about the rest. Okay? Why is the rest there? The rest is there because maybe some of these have some special stereochemistry, wedges and dashes, or regiochemistry, where the groups go on those carbons. That's why those extra pieces are there, to help accent that. Wedges and dashes. Okay? So those wedges and dashes establish our stereochemistry. Regiochemistry, this red reaction, what did I add? I do accept strong acid. What were the groups, what were the pieces, atoms added to the structure? Bromine, yes. And?
Hydrogen.
Also added a hydrogen. Orange reaction, what did I add? HX, X standing for halogen, so let's make that a bromine. What did I add to that structure? A bromine and hydrogen. What is the difference between the red answer and the blue or orange?
The red.
That's the regiochemistry. Where did the groups individually go? What are you going to add?
I was just saying that in the orange one, the bromines on the more substituted carbons. So.
Okay. So in the orange one, we have the bromine at the more substituted position. Okay. Long time ago, before we knew about electrons, some dude looked at these reactions and said, when I add acids to these alkenes, I notice that the hydrogen goes to the position that has the most hydrogens. Like all the time. That's amazing. That was so cool that he could predict that before we understood electrons. So to honor him, we associate a name of the addition reaction. Markovnikov. Okay, that's cool. We didn't understand electrons. Do we know what an electron is now? Yes. Let's look at the electrons instead of some long dead dude's name. Okay? Because his reaction failed here in red. Okay? And one of the most common things students will do, if you're right, so it's okay. Markovnikov addition versus anti-Markovnikov addition. You mean you have no clue what was going on, you're just listening to some long dead Russian dude. Okay. You're right, so I got to give you points, but you can't use that knowledge anywhere. Understanding how the pieces fit, a lot more important. Okay? We also get some oxidation reactions. Okay? So these are looking at an alkene again. Notice I'm taking the same structure, new reagents, and it new spiders out. Lovely. Don't we love spiders? Like they make cool things. Okay? Unless they're on a variety of drugs. Caffeine, I think, is the worst. Addition reactions. Okay? Adding hydrogen. Okay? Doing a reduction. There are a variety of reagents that we could use for those. Notice that we have some differences between these. My personal favorite, we add things like Lindlar's catalyst. What is that? Something special. It's another thing like Markovnikov. That's cool. You came up with something phenomenal. How about you show me the chemistry? Okay. The chemistry there is looking at your palladium or platinum salts with something else added. That something else is usually something like a barium sulfate, calcium carbonate. It kills the reactivity of the reagent and it stops the reduction partway along. Okay? So there's a variety of ways these things can pop up, and you'll see different names associated with them. Just look them up. Okay? Don't freak out at those names. This one's just weird. Why is this one just weird? We double back. All of these additions happen with the hydrogens getting added to the same side of the pi bond. Why is this one weird?
Because it's opposite.
They're adding on the opposite side. Why else is it weird?
Because it doesn't go all the way. Oh,
Uses
you don't have
associated.
H2.
Where's the H2? Where's the hydrogen I'm adding?
Nitrogen.
It's coming from the ammonia. Okay. Well, if I'm going to add two hydrogens to a pi bond, one has to be positive, one has to be negative, right? Because the pi bond is just a source of electrons, positive, negative. Hydrogens from ammonia will always be positive. How do I do that? That's kind of a goofy reaction. It's a goofy reaction that involves radicals. Okay? Through this fun little radical mechanism, it's neat, it's cool, I like it, but that's about it. Okay? So if you're interested in looking at the basics behind that, I can talk you through all of that at a future date. Okay? Where we will talk about that in a little bit more detail is when that same reagent is used with benzenes. And what can you tell me about benzene chemistry? How reactive are benzenes? Not. Okay? And for the majority of this semester, that is your answer. Benzenes do not react. Okay? Unless we do really special chemistry with them. One of those special chemistries is throw sodium metal at it. Sodium metal in the presence of ammonia, it will reduce benzene. Okay? That's how reactive sodium is. Excuse me. It does it in very particular patterns that follow the same heart of the mechanism for the alkyne reduction as well. Okay? And we will look at that very end of the semester, probably like the last week. Which then gets us into our addition reactions with acids. What do we expect as a product? Addition, good. Why addition? We see a pi bond. So if we do an addition, what should happen to the pi bond? It should break.
Form a carbocation.
Okay? Didn't ask for a mechanism. I will get there, but yes, I like it. We add a hydrogen and we add bromine. Where should they go?
The hydrogen goes there. Red.
Red or blue? Well, we listened to that long dead Russian. It is a Markovnikov addition. Blue is the answer. Okay? And literally by saying that, what we're doing is that some dude just observed a bunch of reactions and said this was the answer. So by you going through and saying blue is the answer because of Markovnikov, you're saying, I have no clue, but I trust this dead guy that I've never met. Okay? You've met me. You shouldn't trust me either. But maybe a little more than a long dead Russian. Okay? What should we be looking at to help us decide which one?
Charge.
We could evaluate our charge size. And in that charge size, that's going to help us decide how we should react. What is the most reactive thing that I'm starting with?
H+.
HBr is a strong acid. This is H plus and Br minus. That is now going to drive my conversation. H plus, face test, don't like, fix it. How do I make H plus not plus?
Add electrons.
Where do I have electrons?
You have electrons in the pi bond.
Pi bond.
It's got to bring in
Okay.
one direction now. So, if you
So
go-
now if we go through, we could place the hydrogen there. Is there anything stopping us yet from placing the hydrogen there?
technically, yes.
Shown?
Yeah.
Not shown. Okay? The mechanism arrow does not allow us to see where the hydrogen goes. The mechanism arrow just says we take electrons from this pi bond and we make sure that those electrons are involved in the bond with the hydrogen. That arrow gets us to both of those structures. We have to understand chemistry to establish which of those structures is more likely. There are two approaches to doing that. One is recognizing that those pi electrons came from one from each of those carbons. I've now taken them both out, and I've shared one with the hydrogen, and I gave another one back to that one, which means that carbon lost an electron and gained an electron. So what happened to its charge? Nothing. What happened to the other carbon? Lost an electron, which means it is positively charged. What happened on the red one?
Same, but switched.
Same process, but I put the positive charge there. I can now evaluate those two possible products that came out of this and decide which one is better. What makes each of those reactive? Charge. Okay? What is that charge?
Plus one.
Positive. What would make it less reactive?
Stable.
What makes it more stable?
You're right.
To become more stable, it needs more electrons to neutralize that positive. So now what I would go through and do is look at those two positions and decide how many electrons are nearby. In both cases, they have 3 bonds, which means they each have, I know it's a really open-ended question,
3 electrons.
6 electrons around them. Each bond holds 2. Okay? No difference there. So we move one step further out. What do we encounter? The different substitution effects. Let's take a look at the red one because it's closest to when I'm walking. Hydrogen has how many electrons? I won't accept 2. There are a couple answers I'd accept, but 2 is not one of them. I'll accept 1 as 1 valence. The other answer I would accept? 0. Why? We already accounted for it in the bond. Okay, so we're just going to go based off of valence. Hydrogen has 1 valence. Hydrogen has 1 valence. What is that?
It's carbon.
That's a carbon with 4 valence. How many electrons around the red carbocation? That was 1, 1, 4. Right?
Yeah.
I'm just making sure we're all getting on the same page. Blue one. Which of those carbocations is more stable?
9.
9. It has more electrons around it. Whoa. I thought that was really cool when I discovered that. You're like, that's old news. That's fine. Just walk all over me. Okay? That's really tedious. Does anybody look at that and go, I got to do that for every single reaction?
Yes.
Kind of, sort of, yes. You can start to come through, jumping through some steps to kind of help out. One way would be to draw your resonance structures. It helps if you actually draw a resonance structure. You could just draw one and be like positive. That puts, which one do you prefer to look at, positive or negative? Doesn't matter. It's entirely up to you. You'll get the same answer. If we look at the positive, that positive is a secondary carbocation. If we switched them, it would be primary. Secondary is more stable than primary. Oh, I drew the right one. That's the one that needs to go through and react. That's now going to tell me where my charges go. That negative goes to hydrogen. Blue structure. What if you drew the wrong resonance? You suck, damn.
Yeah. I was gonna say you're a shit.
Ooh, primary positive. Oh, that was horrible. Primary positives aren't stable. It should be a secondary. Scribble, scribble, scribble. Do the other one. Ta-da! You don't have to draw multiple structures. You just have to recognize that internal switch. Okay? Now what do we have? We've got a positive carbocation and negative bromide. What can we do? Tack. And we end with our answer. Make sense? Electrophilic addition with acids.
When is it the other way?
Whole chapter. When does it go the other way around? When the electrons align to set up the charges that way. Ultimately, the only way you get that one is when you do something kind of crazy and a bit bizarre, kind of out there. You might call it
I mean, if you reacted with
radical.
something else.
The only reason you'll get that substitution with a HBr is if you run a radical mechanism, which I think is actually in the subsequent slides. Okay? What happens if we do an alkene? It's an alkyne.
Same thing.
Same process. Nothing changes. It's still a nonpolar pi bond. We go through, we put the bromine at the more substituted position, hydrogen, ta-da. What do we have in that answer?
The next step.
We have a nonpolar pi bond. What does HBr react with?
Non-polar pi bond.
Nonpolar pi bond. So what happens?
Runs again.
We do it again. Do I have to show the hydrogen? No. And in fact, arguably, this structure is wrong. Okay? If you draw that in SmartWork for sure, it says you're wrong. Once you have specified one hydrogen at a position, you better specify all of the hydrogens at that position. This is now correct. This is now wrong. Still wrong. Now correct. Okay? Make sense? It's a subtle thing. I understand why SmartWork wants to do it. I don't necessarily agree with it, but there's a bunch of stuff that I don't necessarily agree with. Okay? So then let's throw another one out there. Does it have a strong acid? Yes. So should this still be doing the same basics of our reactions? Yes. What was our nucleophile up here? Br minus. What's our nucleophile down here? OH minus. What does OH minus act as? A base. And in particular, what type of base is OH minus? A strong base. What is H2SO4? Strong acid. Is OH minus the nucleophile? No, because I'm now putting two competing things in the same solution. You run into trouble with that. I know where you're going. The oxygen is your nucleophile, not OH minus. Okay? So what you are suggesting is that we would go through this process, alkene, OH. Yeah? Same basic patterns. Okay? Still an alkene, so we could do it again potentially. Cool?
No,
Which of those is the right answer?
neither.
What happened?
Like keto-enol tautomization.
This is an alcohol connected immediately to an alkene. And for those of you being like, we have to memorize that extra fancy functional group, that's silly. What functional group did I just draw? That's a carboxylic acid right there. That's a carboxylic acid. That's an alcohol. We've got a couple gray area, all except a ketone. Officially, we need to see the carbons out there. You mean that's not an alcohol and a carbonyl? It's a carboxylic acid. Why is this now a carboxylic acid and not the sum of the two parts? Because their chemistries affect each other. Are these connected to the same pace? Do their chemistries affect each other? Yes. This same functional group is just like a carboxylic acid in that the chemistries overlap. What we've got here is a little bit better of a name than a carboxylic acid because no part of carboxylic acid sounds like alcohol or ketone. What we have is an ene-all, alkene alcohol. If we end with an alkene alcohol, guess what happens? We run through a tautomerization. Look it up. You can figure it out. The TAUT is good enough. And we get the ketone. It was known as a keto-enol tautomerization. Why? Ketone, enol tautomerization, the oscillation back and forth between them. How important is that chemistry? Because that's just goofy. We don't have to want to deal with that ever again. All of biochemistry is that reaction. Okay, so you got to move into biochemistry. That's it, right there. You don't even have to take biochem now. You know it. You're welcome. What happens if we have something like this? Strong acid, alkene. Why is this one different than the past one? It's a diene. There's two alkenes. Okay? Are those pi bonds different from each other? No, so who cares? Let's just react one. And we have our answer. Mike has kind of said that mechanisms are important. Maybe we should slow our roll. Positive charge, that's a carbocation. And whenever I see a carbocation, I should think two things. Both of them begin with the letter R. Resonance and rearrangement. Okay? We don't have a rearrangement issue popping up here, but we do have a resonance. And what is your response to that red structure?
I like it less.
You like it less. And of course, my response to your answer is?
I don't care.
A bit heartless. Not I don't care. Why?
Because you've got less. I mean, there's still, it's okay because of the resonance. Because the resonance stabilizes it more. I would say like 60-40.
This is that substrate thing that comes out. You're like primary versus secondary. Primary sucks. Don't ever form it. That's primary with resonance. That structure is better than a tertiary structure. That's not a bad structure. That's a really stable carbocation. Not as stable as that one, but that's a really stable carbocation. Okay? Because it is stable, what can now happen?
You can attach the bromine. Or the bromine makes an attack.
The bromide could attack to either one of those, resulting in two possible products. Yeah? Okay, we'll call it product A, product B. Remember, you guys just told me the red one sucked. Which structure is the answer, A or B? Oh, you're hedging your bet. Depends on the conditions, you jerks.
What are we wrong?
B is more stable than A. But B came from the red structure that sucked. Why is B more stable than A? Thermodynamics is the same thing as saying it's more stable, so I don't quite accept that.
More energy.
That's the same thing as thermodynamics. It's fair. What makes both of these structures reactive?
Pi bond.
The pi bond. Which pi bond is more stable? The more substituted one, because it's not charge, it's not size, it's not electronegativity, resonance, induction. It's now substitution patterns. This pi bond in B is more substituted than A. That makes B more stable than A, which means B is a thermodynamic product. However, to get B, I have to pass through a very high energy intermediate, which means it doesn't form very fast. So A might form faster. So instead of it being a thermodynamic product, it might be kinetic. We have to deal with kinetics versus thermodynamics. Okay? This will pop up again and again and again and again. Okay? We've actually already talked about it a couple times earlier. You just didn't realize it yet. Okay? With that, we have to be done. If you got questions, you can ask, but we're doing better with timing.